Excellent.
Thank you.
Thank you very much for having me. I'll take the clicker.
Please.
I've never seen so many developers in suits. It's amazing. Actually, that's not true. I know where all the developers are. Those are where the empty chairs are. So they're like I should be, which is still sleeping in the hotel. But 9 a.m., awesome. Just kidding. It's okay. I know you guys have like really strict, rigid policies where you work, but you can, I mean, I work at Goldman Sachs. I can laugh about it. You guys can laugh about it too. We're going to go through an incredibly complex topic in a very simple way in a very short amount of time, because I'm going to try to keep us on schedule, and also because I told him, eat up as much of my time as you want, so there's no room for questions or anything, so great job. Basically, I'm managing director at Goldman Sachs. I came to Goldman Sachs through the Honest Dollar acquisition. I'm also the chair of the IEEE's Quantum Computing Standards Work Group, as well as I do a lot of other volunteer activities in that area. And today we're going to talk about quantum computing. I love it, maybe a little too much. It's become an obsession of mine. Everybody at work is tired of hearing about it. I've been dealing with it for about 5 years. I've been making investment of time and money and other things for about 3. And for about the last 16 months, I've been really, really super onto this. But warning, not Neil deGrasse Tyson, so, or Brian Greene. Are there any physicists in the room? Just so I have a heads up. Where? 1, 2, all right. Are you a theoretical physicist? Think about it. See, it says, are you really here? Think about it. We will not take questions from anyone then. So here's the deal. How do you prepare for a quantum world? I kind of have a personal superposition for this because I feel like my career has both prepared me and not prepared me at the same time. Didn't do a lot of computer science, didn't do college, didn't do a lot of physics, obviously, but came out of Apple R&D, came out of IBM Research and Development, ran some labs in Haifa and Zurich and some things, and I felt like, man, I'm really prepared for this. But turns out it's really difficult. So I have this is my 21-month-old at 17 who prepared me for this because he has an amazing library, including this book by Chris Ferry, which is Quantum Entanglement for Babies. It's a real book. It's not Photoshop. And basically, future parenting problems. So when I heard about that, I was like, I need you to get your team on quantum computing for babies immediately, which he did. And so while that joke of his class drawing is a thing, at South by 2018, we'll release 2 books, Quantum Computing for Babies with Chris Ferry, which sounds, I know this sounds offensive, it's not meant to be, but it has turned out to be the best explanation of quantum computing ever. The way that went down is I was like, Chris sent me the template, starts with this is a ball, ends with now you know quantum computing. I said, I'm gonna knock this book out with a rum and coke tonight. And then 6 weeks later, I was like, God, we're on page 13. Because turns out simplification, super hard. But there's 3 things I want you to get out of here. 3 concepts, 2 comparisons, okay? I want you to understand quantum tunneling at a super high level, not like these guys. I want you to understand superposition at a high level, and I want you to understand quantum entanglement. And then I want you to understand some classic versus quantum differences. Most of you probably only work with classical compute architectures right now, unless any hedge funds in the audience? No. There's 3 of them that are working with quantum, but obviously not here. So we're going to start with a brief history of computing for those of you who don't really geek out on all of the details. Starts with an abacus, goes to the ENIAC in 46, then we get to this thing in 65 called Moore's Law. You're all familiar with that, and we are all tired of hearing about it, but I must throw it into the deck because it is important if we're going to talk about it slowing down and how fast quantum computers are going to be, et cetera, et cetera. But basically, after 65, you got to the Altair, then the Apple, then the IBM personal computer, the iMac, it goes on, and the J-phone. Anybody remember the J-phone at all? Coolest people in the room. That was your original like super smartphone SoftBank put out. And then in 2007 you had the iPhone, and now you have the Google Pixel that I got at this year, but now you also have the Google Pixel 2. So let's start with quantum tunneling, and let's take those devices and kind of put it into perspective. So basically size matters. If you look inside a chip, we got a circuit, right? We've got some modules, there's some gates, we're all familiar with those. And basically, this is how we process things. Now, the way we process them is simply by stopping a flow or letting it go through. So that's a 1, we stop it, it's a 0. It's pretty simple. The problem is that we are getting smaller and smaller and smaller in the technology. But if you think of a transistor as a basic unit of a computer, then if I had enough Julians and he could do enough remedial math, I could calculate anything, right? From astrophysics to Zelda, it doesn't matter. But I am getting a new Pixel 2 XL, and here's the interesting thing. That is a Snapdragon 835 processor in it. On that processor are 3 billion transistors, all right? There's a picture of it next to a penny, but the key takeaway is that we're going from 10 nanometers to 7 nanometers to 5 nanometers. So the question is, at what size do we get so small that things start to break down and quantum tunneling comes into effect? So we send that down, and it just decides to go right through our gate and appear on the other side, and computing as we know it potentially breaks down. Depends on whose side of the argument you're on this, but it's obviously going to present some challenges on the quantum mechanics level. What is the big thing everybody talks about with quantum computing? Quantum superposition. Okay, so it's all ones and zeros till somebody gets hurt. But you have a 1 or a 0 in a bit in a classical system. You have 1 and or 0. That's because you're talking about the spin of a particle, electron, photon, whatever. But as it spins, spin up is 1, spin down is 0, and it becomes really interesting. Things computationally take on a new form, and the reason that they do that is because of the fact that if we look at it, it can theoretically represent a 1 and or a 0 at the same time. So what are the advantages? In a classical system, we have 2 bits, we add 2 bits, we have 8 outcomes, but in a qubit-based system, if we have 2 and we add 1, we have 2 to the n of the classical bits. So the computational power potentially grows exponentially. Now, that also leads to how do we measure this in a system? Instead of a normal classical architecture where we measure everything measure by measure by measure. Because of quantum entanglement, Einstein called it spooky at a distance, we can potentially measure bits by knowing the state of another bit. Now, China is using this to build quantum communications right now. So they're super encrypted communications. They sent up a satellite called Minkus. This year, they actually sent to entangled particles 1,200 or 1,700 kilometers, depending on which report you read. And that is super, super exciting for communications. It's also super exciting for computing because it gives us the opportunity to measure something without having to go through and measure everything in the system. So what do I want you to remember about entanglement and superposition? Entanglement, you know, everybody's worried about quantum computing and encryption, and I'll get to that if you're interested, but the entanglement is the fascinating part to me. And the superposition is not as exciting as everybody makes it sound. It's cool, we get it, you can calculate more stuff, but I think the entanglement's gonna prove to be a bigger advantage. Remember that you do not get away from a classical architecture when you use a quantum computer. You have to have a classical computer that preps the data, does the input-output into the quantum system. So you're not getting away from that. I know Google's been preaching about the quantum supremacy. A lot of people have been talking about that. There's not a quantum supremacy to me if you have to attach a classical computer, like appended on the side, right? It doesn't sound super exciting. But here are the two things that I want you to get. Number one, much like Facebook statuses, it's complicated. In classical theory, you have a state of bits, it's total of multiple bits. In quantum, it is greater than the sum of its parts. These systems are very small right now. They're 5 qubits, 7 qubits. IBM recently did an experiment where they broke the theoretical 49 qubit simulation and they did 56 qubits. And that was super exciting because I think we're going to be simulating for a few more years, so good for them. But the other thing is, everything can be copied in a classical compute architecture. The main difference people fail to understand about quantum computing architectures and classical computing architectures is that in a classical system, you can copy the data. That's how we manipulate it. In a quantum system, we can see the results of processing the data, but we can't copy the data itself. So think of it like Schrodinger's cat, right? A classical computer we can look at, we can see the gates, we can see it working. A quantum computer, we put everything in, and we get a result out the other side. And there's two forms of quantum computing right now. There's quantum annealing, and there's circuit gate modeling. The circuit gate modeling is a little bit more like how we traditionally think of computers working. The annealing gives you the best answer most of the time that's probably right. So an example is, if you're at Berkeley or somewhere right now, you can factor 15, and it's 3 times 5, 48, 49% of the time, okay? That's okay because these machines are used for a lot of probabilistic things. So if you look at what are people doing with quantum computing in finance right now, quantum Monte Carlos, right? You could do some really interesting things with pricing complex derivatives. There's a lot of things that you could do. But how is this going to affect finance? So right now, there's a few people using it. There's not enough people. I would encourage you all to use it. But it's going to affect finance because if you think back to the days, if you read Michael Lewis's Flash Boys or any of those books about high-frequency trading, there was this period, this gap, where all of a sudden somebody could execute a trade faster and there's billions of dollars hidden in those little speed advantages. That history is just going to repeat itself into finance with quantum computing. Somebody's going to get access to a quantum computer, they're going to be prepared for it when that access becomes available, and they're going to take advantage of that access financially. It is literally that simple for you guys. The difference is how big the gap is between I can trade really fast and all of a sudden I can calculate billions of things in the time that it takes you to calculate 3 or 4, right? It's going to be a much, much larger delta between where we're at and where you'll be with the quantum computing. So let me give you an example of that. Death of a salesperson. Everybody know this example? So I have a computer that does 10 to the 9th operations per second. And I have a salesperson I want to send to 14 cities. Pretty simple problem. It takes that computer, it's 10 to the 11th problem, 1,000 seconds to process that. If I increase the number of cities from 14 to 22, it takes that same computer 1,600 years. Because some problems are deceptively done. Now, people have argued they found ways around the problem, just like Moore's Law, right? This is the Moore's Law of my area of the industry, right? Everybody's like, oh, no, I found a way around it, I found a way. But if you went from 22 cities to 28, it would in theory take longer than the known universe to come up with the best route, okay? These are problems that have hidden complexity. Finance are math problems that have hidden complexities. This is where something like a quantum computer would shine. Why? Because let's say I'm searching a large database of information. I only need the square root of the number of entries to get to the same answer you had to process everything through. So why is Google interested in quantum computing? They're a giant database. It's obvious, right? There's a bunch of other stuff, but I mean, there are obvious technical advantages for them to have it. Microsoft just announced that they're going to have a quantum computing development kit in Visual Studio, and that they're doing a quantum computer. Now, their quantum computer is different. We talked a little bit about annealing versus circuit gate models. The thing to know is that there are multiple ways you can build an actual quantum computer. Rigetti Computing has their way, IBM has their way. Microsoft's way is that they are working to discover an anion. And when they discover that particle, then like quantum computing magic. It's actually very interesting. They're most likely to be the ones to win like a Nobel Prize or something out of their work. And I'm not a huge Microsoft fan, but kudos to them. That's amazing work. So who's working with it now? I mentioned some hedge funds. Let me give you an idea. Renaissance Technologies, Deshaw, and 2 Sigma were both featured in the press this week. They are using quantum computing to do ways of testing investing, of testing outcomes of investing, of doing these things. And then, you know, the big question, why are we here? Where's the open source? So this is the problem. It is hard science, and a lot of hard scientists do not understand open source. And so I've been spending the last few months with the IEEE working on the standard side. I've also been trying to help the Linux Foundation and others to create an open source project around that. I'd like to see Symphony Foundation do an open source project around quantum and finance. And so my role right now is to try to bring that community together. Now there are open source projects. Rigetti Computing has, you know, Forest and several other tools out. Google just released a compiler that you can use to do chemistry. There's protein folding projects, but there's not a lot in the area of finance yet. But my warning to you is that I think that by this time next year, there will already be a lot. There'll be open source quantum Monte Carlos. There'll be open source a lot of quantum stuff. I know people who are working on the projects. I think that the quantum computing hype cycle is kind of went up and kind of leveled off, so I don't think it's a lot of overhype about the doom. Now, when you see the speed things, one of the projects we're working on is a performance benchmark, right? Because if you go and you study this after you hear me talk, you're going to notice that, don't make that buzzer go off because I'm on the last slide. All right, he's still going to make it go off. The speed difference, we don't know what it is. We just know it's potentially exponentially greater, and for the most part, it's faster. right? It's very difficult. You go see D-Wave put out a study, and I love Bo and the guys at D-Wave, but they put out a study, and then Scott Aronson, who was at UT, writes a paper that says that math is all wrong. And there's some of you that will get that math. I work with a lot of smart math people. If you're not a discrete mathematician, probably not interested in reading any of those papers. But I think what you're going to see before the end of the year is a massive collaboration between these tech giants in the space of open source. And what I wanted to end with is two things. One, if you like this t-shirt, because apparently not enough of you own t-shirts, I'm very concerned about this in the financial industry. I think you only have suit jackets and shirts. Then I brought some t-shirts to give away. And if you go back and see Jackson, this guy here in the shorts, also obviously a developer, he'll be happy to give you one. We brought some ladies' t-shirts, and we brought some men's t-shirts. I don't know how many we have, but we have like 2 or 3 of each size. But if you go to superposition.com, if you pay attention to it, that's where I've started blogging about this. That's where I started talking about it in very simple to understand ways. It is not a science blog. It is simply an information blog where if you're interested in quantum computing, especially in the open standards or open source area, you can get some resources. And with that, I'll turn it back over to the crew. Thank you very much for having me.